Hello, everyone. Before introducing him, I want to tell a few things. That was the first time that I attended this program. Eda invited, and thanks to Eda, especially Eda, and the other organizer, of course. That was really a good experience for me. And Berat also, this was the first time for him, and we enjoyed, I believe this. And he's a third-year student in mathematics engineering at Istanbul Technical University. Now your turn, Berat, you can continue.
Hello, everyone. First of all, I want to thank you, the organizers, for this program, and I also want to thank my mentor. The topic of my presentation is Diophantine m-tuple, and I divided my presentation into two main parts. First, I will make an overview about Diophantine m-tuples and Dn m-tuples. And this topic includes what is Diophantine m-tuple, where they come from, how large these sets can be, connections with elliptic curves, and also Dn m-tuples. And at the second, I will talk about our main article, strong rational Diophantine DQ triples. Okay, let's start. The story begins with the Greek mathematician Diophantus of Alexandria. Diophantus finding four numbers such that product any two of them and increase by one, it's a perfect square. And this is a Diophantus set. For example, if I multiply 1/16 and 17/4 and add 1, and this is 9/8 square. And this is true for any two of them in this set. But as you can see, these all four numbers are rational. And after Diophantus, Fermat finds four integers with the same property. And this is maybe the most popular set in this topic, 138 and 120. For instance, if I multiply 8 and 120 and add 1, and this is 31 square. And here are the definitions. A set of m-positive integers with ai, aj plus 1 is a perfect square. And a and j must be different from each other is called a Diophantine m-tuple. And if these numbers are rational, it's called rational Diophantine m-tuples. And now, how can I extend these sets? Let's say I have a Diophantine pair, and this is A and B. That means I have one equation. AB plus 1 is a perfect square. Let's say this is R square, and I want to extend this pair to triple. And I easily do that just adding A plus B plus 2R. And here's an example. If I have 2 and 12, my third number will be 2 times 12 plus 2 times 5, and this is 24. And also, if I have Diophantine triple, I can extend to Diophantine quadruples. And this is my perfect square equation. And let's say my fourth number will be D, and D is equal to A plus B plus C plus 2ABC minus or plus 2RCT. As you can see, D can be two different numbers, depends on plus or minus 2RCT. And you can see here an example. And if I will get a Diophantine quadruple in this way, I can say these are regular Diophantine quadruples, but most of the mathematician believes all the Diophantine quadruples are regular, but this is not proven yet, just an open conjecture actually. Okay, we talk about pairs, triples, and quadruples, and now we can now ask how large these sets can be. Is there any Diophantine quintuple, sextuple, or these sets are infinitely large? And we know the answer for integer case, but we don't know the answer for rational case. Now, there is no acceptable upper bound conjecture for rational case, but these questions are related to elliptic curves, and elliptic curves actually, this topic makes more interesting. First, look at the integer case. We know it's easy to prove that there exist infinitely many integer Diophantine quadruples because there are parametric families involving polynomials and Fibonacci numbers. You can see here an example. And also an old conjecture in integer case named folklore conjecture. This conjecture is not published, but most of the mathematicians believe this conjecture is true and states that there does not exist a Diophantine quintuple. And after that conjecture, in 2004, Andrea Duella proved Diophantine sextuple does not exist, and also proved that if exists, there are only infinitely many Diophantine quintuples. After Duella, many mathematicians worked with Diophantine quintuples with boundaries, and in 2019, 3 mathematicians proved there are no Diophantine quintuples. And this is the end of the integer case. Now we know there are infinitely many Diophantine quadruples, but there are no Diophantine quintuples or sextuples. Now we can move on to integer case. After Fermat, Euler showed that Fermat set can be extended to Diophantine quintuple by adding just this number. I can't do it now because too big, the numerator and denominator. And also he showed that there exists infinitely many rational Diophantine quintuple. And in 1999, Gibbs found the first example of Diophantine sextuple. This is Gibbs' set. And in 2019, a couple of mathematicians proved there exists infinitely many rational Diophantine sextuple. But today, there is no example for Diophantine septuple. And for that reason, this case is still not closed, still remaining, and still study about that. And maybe the most important question about Diophantine m-tuples is there any Diophantine septuple exists? Now we can talk about Diophantine m-tuples and elliptic curves. Let's say we have a rational Diophantine triple, and that means I have three perfect square equation, and I want to extend this to quadruple. And let's say my fourth number will be x, and x must satisfy ax plus 1 is a perfect square, bx plus 1 is a perfect square, and cx plus 1 is a perfect square. This is a perfect square notation. And if I multiply these three equations, actually I will get an elliptic curve equation, and my all multiplier must be perfect square, and this is actually related to double points on elliptic curve. We will see in the article much more detail. Okay, until here, I multiply two numbers and add one, but now I can replace number one with a fixed integer n, and this is a new definition. Let's say n be an integer. A set of n positive integer is said to have property dn if ai aj plus 1 is a perfect square, and a and j must be different from each other. We can say Diophantine m-tuple with the property dn, or shortly I can say dn m-tuple. And I want to talk about Diophantine quadruples with the property dn, and this question is almost completely solved. The first part of the question, if let's say n is the integer and n form is 4k plus 2, then there does not exist a Diophantine quadruple with the property dn. Actually, this is a very simple proof. You can see easily. Just work with the modulo 4, and this is a actual contradiction proof. Also, second part of the answer proved by Duella again. If an integer n does not have the form 4k plus 1 and is not the element of S, you can see the S set of S in here. These are exceptional numbers. Then there exists at least one Diophantine quadruple with the property dn. And there's a conjecture also here. If n is the element of S, there does not exist a Diophantine quadruple with the property dn. And this is the first part. Now, I will try to summarize the article that my mentor and I worked on over the summer. And this article, including introduction part, construction of strong rational Diophantine DQ pairs and triples, very long proof, and some example. And the title of the article is Strong Rational Diophantine DQ Triples, and written by Andrea Duella, Matteo Paganin, and Mohammed Sadi. Okay, we already know that the definition of Diophantine m-tuple states that ai and aj plus 1 is a perfect square, but a and j must be different from each other. And after this, Duella and Petrovich make an addition to this definition and say ai square plus 1 is also must be perfect square. And this type of sets are strong rational Diophantine m-tuples. And they also prove there exist infinitely many strong rational Diophantine triples. You can see here an example. Now, this brings us to a new definition. Let's say Q be a rational number. We have a set with m non-zero rationals, and such that ai aj plus q is a perfect square. But now a and j can be equal to each other. And this is a strong rational Diophantine DQ m-tuple, rational Diophantine DQ m-tuples. And this is the main theorem of this article. We want to show, we need to prove that in this article. There exist infinitely many strong rational Diophantine DQ triples for infinitely many square free integers, and we will see why is square-free integers Q. And let's say we have a strong rational Diophantine DQ m-tuple and multiply with one coefficient. Let's say Z in here. And this is also strong rational Diophantine m-tuple. But there is one difference. DQ m-tuple will be dz square m-tuple. And for that reason, I need to show the existence of strong rational Diophantine DQ triples for square-free integers Q. And before the beginning to proof, I need to make some parameterization. And I can say Z is equal to 1 over A1 and A1 is equal to 1. And Q will be R square minus 1. This parameterization is important because calculations is much more easy with that parameterization. This is the importance of this parameterization. Okay, this is my first proposition, and my aim is construct strong rational Diophantine DQ pairs and show that there exist infinitely many strong rational Diophantine DQ pairs. Let's say my pair is 1 and B, and that means I have three equations. First one is 1 square plus Q, and I know Q is equal to R square minus 1, and 1 square plus Q is R square, and this is a perfect square, no problem. My second equation is B square plus Q, and my third equation is B times 1 plus Q. And I have to find the B. And if I replace B with the X, my equation is X squared plus Q and X plus Q. And if I multiply these two equations, I will get an elliptic curve equation. Okay, first I need to make sure of that this elliptic curve is non-singular. And for non-singularity, I look at a discriminant of this equation, and he said Q is not equal to 0 or minus 1. And Q is not equal to these values, or is not equal to 0, minus 1, or plus 1. And you can see here some obvious rational points on elliptic curves, T, P, and S. In the proof, I will take one of them and show these double points as infinite order. You will see why. And here's an important sentence. For any rational number B, such that 1B is a strong Diophantine DQ pair, is the X coordinate of a point on EQ. But my aim is the opposite direction of this sentence, actually. I will try to prove that X coordinate which the points on EQ gives us to B, actually. There is some points in elliptic curves is related to B. And this comes from actually standard two distant yield theorem. This theorem is an if and only if statement. If we have, if my elliptic curve equation multipliers are all multipliers are perfect square, and that means I have double points, and double points satisfies the 1B is a strong rational Diophantine DQ pair. And after that, I work with the double points, and I need to show these double points are infinitely many. And for that reason, I need to prove this elliptic curve has rank at least 1 over Q. And that means if I have one double point, this double point has an infinite order. Actually, you can say you can do that for every point in elliptic curve. But my aim is work with double points, so I need to show that my double point is infinite order. But I can't give much more detail here because this proof takes so much time, and I will skip here. But my main aim is AQ has rank at least 1. Okay, by the proof of this proposition, I can construct some strong rational Diophantine pair families, and you can see here an example, 1 and 5 over 4 minus R square, and I will use this pair actually in the next proposition. And this is the second proposition. My aim is construct a strong rational Diophantine DQ triples. And if you have a strong rational Diophantine DQ triples, you have 6 equations. And I need to show that these all equations are perfect square. And as I said, I know that Q is equal to R square minus 1, A is equal to 1, and B is equal to 5 over 4 minus R square, and B comes from the pairs actually. And I can say C is equal to S square minus R square plus 1, and that comes from this perfect square equation. And I assume S is equal to K times R. And from that parameterization is actually automatically A square plus Q is a perfect square. B square plus Q is a perfect square. And there's only left two equations. I need to show that BC plus Q and C square plus Q is also a perfect square. And let's start with BC plus Q. And with parameterizations, BC plus Q equation now looks like this. And I need to show this equation's discriminant must be 0. And this is the discriminant of this equation. And for the makes this discriminant 0, K can be equal to 3 over 5 minus 3 over 5, 1 or minus 1. But at the same time, this K value this K value can't be, I can say. Also with this K value, C is not equal to 0. And for that reason, I need to choose K is equal to 3 over 5. And with this 3 over 5, my equation will be perfect square. And there is only left one equation I need to show. C square Q must be a perfect square also. And with the K value, my new C is equal to minus 16 over 25 R square plus 1. And this is my C square plus Q equation. And I know that 1 over 625 is a perfect square, R square is a perfect square. So I need to show 256 R square minus 175 is also perfect square. And to show that, I can equalize this multiplier to a perfect square, and this is 16R plus 25T. And with that equation, my new R is this. And with using this R, I can finally obtain my triple. And this is the final form of my triple, and this is the final form of my DQ. And you need to be careful. T is different, must be different from these values because these three numbers cannot be equal to each other. And for that reason, T is not equal to these numbers. Okay, now we construct the strong relation Diophantine DQ triples. Now we only need to prove that for infinitely many square free integers Q, there are infinitely many rational numbers T. And I equalize this to QV square for some rational number V to get a quartic curve equation. And if I multiply all numbers with V, I also get a strong rational DQ triple. And if I divide it by V, I can get rid of the 140 square. This is also perfect square. No need to work with this multiplier. And this is my quartic curve equation. And I also work with the quadratic twist of the curve. I can't give any detail here, but this is needed for the proof. And with some parameterization, I will get an Weierstrass equation. And I want to do this actually because I work with elliptic curves. And if I work with elliptic curves, if I show that elliptic curves rank match at least 1, this proof will be finished. And this proof also not be finished in here, makes much more detail, but this is too long, so I can't give in here. But the main idea is to show that EQ rank has at least 1. Okay, and this is the motivational part. You can see some Q, A, B, and C values. And with these values, you can construct your own strong rational Diophantine DQ triples. And for more information, you can visit Andrea Diolle website. He is a very important mathematician for this topic. You can almost find everything about this topic in his website. Also, you can find the article we studied with my mentor in this link. And that's it. Thank you for listening.